Hello, everyone. Welcome you to study lecture 1 of module 1. So the title of today's lecture is task planning. Before we enter into the study of today's lecture, let's have a quick review about the learning objective of this course. So this slide tells you that the learning objective of this course is for you to become a designer of a robot as a product. In general, as a designer, you may have at least 4 questions in mind. Question number 1, who are the user? Question number 2, what are the needs of the user? Question number 3, what are your robots which could meet the need of your user or buyer? Question number 4, what are the solutions behind the design of your robot? Here you may face 2 scenarios. The first scenario is in which you know the specific user, you know the need from your specific user. Therefore, you should be able to answer the first 2 questions. The second scenario is the case in which you do not know the specific user. Therefore, you do not know the need of a specific user. However, you still want to design robot as a product which could be purchased by many potential buyers. Okay, so these 2 scenarios correspond to these 2 situations. First situation is the case in which we have a buyer or user who look for product or system. The second case, the second situation is the case in which we have a product or system which look for buyer or user. Okay, so therefore, as a designer of the robot, you may want to produce or design robot, produce robot in advance, and then you try to sell your product to as many users as possible. Therefore, in this case, you need to know who will be the generalized user, what will be the generalized need. Okay, so with this answer, then you will be motivated to proceed with the design of your robot and the implementation of your robot. All right, so the purpose of module 1 basically is for you to identify, generalize the user and generalize the need. And based on the generalized need, then you could proceed with the design of your robot, implementation of your robot. Then subsequently, you can try to sell your robot as many as possible. All right, okay, so that is the situation that we are in. Okay, so we try to come out the product first, okay, and then look for buyer or user. All right, and once we know the generalized need and the generalized user, therefore you need to have the knowledge and the skill to come out the blueprint of your robot. So this slide basically shows you the generic blueprint or functional flow diagram of a robot. Okay, by now, if you do not understand the meaning of this drawing is okay. But after the study of module 1, at least you see the title of module 1 is here. You will be able to understand this module. Okay, but for this module, we are not going to cover in this course because this module will take up 1 semester for you to study. Okay, so slowly you will be able to fully understand this slide. And for example, module 2 are here. Module 3, you see module 3 will cover kinematics, dynamics, and the module 4 will cover robot control. All right. So in order to fully understand the module in this blueprint of a robot, then you need to study all the topics which has been grouped into 4 modules. So today we start with the first lecture in module 1, and the title of module 1 is Robot Man and Design. All right. And the key takeaway from module 1 is for you to know the answer to generate or generalize the user and generalize the need from your generalized user. Okay, so you will see we have a path planning, trajectory planning. Therefore, you understand robot is just a motion provider. Okay, so you can design your robot in advance, then look for user, look for buyer of your product. All right, okay. So then we move on to study the lecture 1 of module 1. Okay, so I will follow this outline to guide you to study lecture 1. First, we start with the purpose of task planning. So because you may have this question in mind, why should a robot to undertake task planning? All right. Here is a definition of task planning. So task planning is a module or process which take a job description as an input and produce a sequence of a task as an output, which are to be performed by robot. All right. So this is like you need to know what are the generalized needs from the user of your product, because without the knowing the generalized need from the user of your product, then what's the point for you to develop or design, implement your product? All right. So this is the starting point, okay, for you to study this course, okay, for you to understand why do we need to design and implement robot as a product. All right. Then in order to understand this definition, okay, or to be convinced by this module or presence of this process or this module, then I will guide you through the answer, okay, to these 2 questions. Question number 1 will be, what are the tasks which could be performed by robot? And this video may help you to know the answer. Okay, so okay, so this video will convince you to believe that the physical capability of today's robot are very, very close to the physical capability of a human being. Therefore, we can deploy a robot to undertake tasks which are actually undertaken by human being. All right. Then next question will be where to find the job for robot to do. And here I give you some pointer to the answers. For example, we can find the job in manufacturing, job in transportation, job in service, job in agriculture, in defense, in education, etc. All right. And here we will use manufacturing as an example to illustrate the procedure underlying task planning, action planning, motion planning, path planning, and the trajectory planning. Okay, so all these procedures are equally applicable to the situation in which robot will undertake a job in other sector of industry or society. All right. Then what is manufacturing? Then how come manufacturing is a very, very popular place for us to deploy a robot? The reason is because manufacturing is a complex system which offer many jobs, which include many tasks for robot to do, for robot to perform. Okay, so therefore this is a very, very strategic domain in which robot could play very, very important role. Okay, then what is a manufacturing system? From here, you just need to look at the input and the output and the inner process. For example, we have inbound logistics. This will be the input to the manufacturing system. Then we have outbound logistics. This will be the output from manufacturing system. And in between, you see production process, transportation. And these include many, many tasks for robot to do, okay? And that depends on the nature of the inbound logistic and the outbound logistic. The job scope will change. Therefore, we may have a different type of manufacturing industry, and their job scope are different. All right. So this is why manufacturing will offer many, many jobs for robot to undertake because inside manufacturing, we can identify many, many tasks, okay, which need the help from robot. And on top of a production line, you see we have a process equipment, metrology equipment, material handling equipment. In particular, we can deploy a robot to undertake process equipment and material handling equipment. Okay. Then on top of the equipment, you see we have a process control, equipment control, material control, etc. All right. And actually, if we lump all this together, this is a kind of operating system of a factory. You know, in a computer, you have an OS operating system. Then in the factory, you treat a factory as a mega computer. Then this mega computer need the operating system. And the name of factory's operating system is called as MES, Manufacturing Execution System. So MES is quite a famous name, okay? And before we can set up a factory, we need to know what is the product or what is the output from this production line. The output basically means what is a product that will be produced by this factory, all right? And also know what is the process involved in the production of the product, etc. Okay, and on top of that, we need to also know how to organize this company, okay? Then how to organize the supply chain to know who are the supplier, who are the distributor, customer, buyer, etc. All right. So this slide basically gives you a big picture about the manufacturing, and this will offer a lot of opportunity for job, for task, okay, needed by your robot, okay, and in particular from this drawing, we can identify generalized job scope, generalized need from the user of the robot, okay? And now I'm going to show you some example, okay, for you to understand that the manufacturing is able to offer many jobs, many tasks for robot to perform.
New technologies are changing the world. They're also making the cars manufactured by the Volkswagen Group more efficient, safer, and more customer-friendly. The nature of car manufacturing is also changing in a similar way. In fact, the next batch of innovations is so extraordinary that experts are already declaring the dawn of a new industrial era, Industry 4.0. So what does manufacturing look like today? Traditional car production involving hundreds of identical vehicles lined up in a row no longer exists. The options available to customers are now so vast that each car becomes a unique and individual object. Cars are now manufactured to order. Data makes its way from the customer's order to the Volkswagen Group's systems and then to each individual section of production. A car consists of many thousands of individual parts. The press shop processes blanks for the bodywork. In the body shop, the car is baptized. In other words, it's given an RFID tag that can track it via radio frequency. This establishes which car body belongs to which customer order. The paint shop also receives information from the system world. In sequencing storage, the cars are placed in an optimal order for assembly. From here, information is transmitted to suppliers and pre-assembly as to which part is required when and where. In final assembly, the finished car emerges. The Volkswagen Group manufactures its cars using state-of-the-art technology, but development and innovation never stop. What does the future hold in store? Today, everybody is talking about Industry 4.0. It is a term used to describe a variety of innovative production processes. But what exactly does it mean? The Volkswagen Group has been shaping the future with groundbreaking projects for many years. Here are some recent examples. Digitalization. The digitalization of all elements of production is essential for a new era in industrialization. Everything is given a virtual likeness in the system world. The result is an Internet of Things. Example, 3D printing. Pressing tools are no longer shaped in a laborious manner. Instead, these tools can be made from steel granulate in a 3D printer. It's a technology that opens the door on completely new possibilities for design, with a level of precision unknown until today. example, human-robot cooperation. In the past, protective grids separated robot arms and employees. In the future, employees and robots will work increasingly hand in hand. This is made possible by new security sensors. Robots take on especially monotonous and arduous activities. Today, robots already play a part in contributing to ergonomic workplaces at the Volkswagen factories in Chemnitz and Salzgitter. Example, big data monitor in logistics. The Big Data Monitor enables for the rapid visual processing of data from the 1,200 suppliers of the Audi factory in Neckarsulm. Where are the potential bottlenecks? Where is the greatest need for action? This data is now easily accessible at all times. The intelligent factory of tomorrow paves the way for efficient and cost-effective production unlike ever before. Industry 4.0 also means brand new opportunities for employees. The Volkswagen Group has already begun actively preparing its workforce for the future. The world is changing, not only in the automotive industry. Everything is in motion, and the Volkswagen Group provides the...
All right, so this short video basically give you an idea about the job in manufacturing, in which you could identify many tasks for robot to perform, right? And this picture basically show you a production line which will produce a car in big quantity. And this picture show you the transportation job in which we could deploy a mobile robot or high-speed mobile robot to undertake the task of transporting people, transporting goods, etc. All right. And in agriculture, this video will also show you there are opportunity for us to identify tasks which could be performed by robot. right. So this video also give you an idea about where to find the job and the task for robot to perform in future, all right? And of course, we can also deploy a robot for medical intervention, medical care, and in particular for surgical operation. Okay.
I'm ready. We make no secret of the fact that we are determined to head right to the top of medicine. That's what we're doing. This is a beautiful example of it. I saw a machine that I'd seen 7 or 8 years ago in a lab building in Germany at Siemens, which was now a reality. And when somebody explained to me how it was going to be used, what more can you say?
We had this vision of what we thought the future of the operating room should be and what the future of surgery should be. And having an administration that was supportive of this future vision, we were able to, with a lot of people's help, create these rooms, which are not only operating rooms that have the state-of-the-art technology, but operating rooms of the future, where we're going to actually change what surgery is.
We're the first hospital in the country to have 2 of these units in the operating room. Just the whole concept of what is surgery or what is needed to treat diseases is changing. We're going to redefine what a surgical specialist is even, because a surgical specialist now has to be an information technology expert. They have to be a radiologist, endoscopist. They have to be able to do minimally invasive surgery. They got to be able to do conventional surgery.
This revolution is really this merging of intervention with imaging equipment that allows us to be better surgeons and allows us to be minimally invasive surgeons.
In this room, at least 12 different image devices so that you can have multiple inputs.
It starts with the electronic medical record. Everyone has access to it. The surgeon has access to it. The anesthesiologist has access to it. The nursing team has access to it. We can communicate with the pathologist upstairs. We have the images from the endoscope, from the microscope. Everything can be viewed at by the clinicians and the people that are taking care of the patient, so we can get everyone's feedback instantaneously.
We're optimizing the patient's care by putting in the hands of the surgeons every conceivable piece of information in the room, helping the physician do the best job for the patient.
And it's not just the surgeon, it's the nursing team, it's the anesthesiologist, it's the whole team.
You notice the attention to detail where the nurse's station over there is. That desk faces the patient. In all our existing operating rooms and in most operating rooms around the country, the nurses' desks and the computers are facing the wall. That certainly adds to the patient safety.
You can always accomplish much more when you bring many minds from different disciplines together. I think that's really the exciting thing about being an institution like New York Presbyterian. I mean, we couldn't have done this without the help of donors like the Helmsley Foundation to mobilize the kinds of resources to build this kind of environment. Basically what this machine can do is if you take fluoroscopy and spin it around the patient, you get a 3-dimensional image. You can see blood vessels in 3 dimensions. You can see solid tumors in 3 dimensions. You can see bone if you're putting in instrumentation and hardware.
By that spinning motion, you can also create cross-sectional images. What you can start to do now is you can start to say, I'm going to operate on the intestine. This machine will give you simultaneously the intraluminal or inside channel picture, and I'm going to be able to see outside at the same time. And this has the capability that we can overlay those images. So you can start to do what I was saying, Jerry. Think about intestinal surgery where the patient doesn't even have to go to sleep. The average patient nowadays is older, more frail, has more serious accompanying diseases. And so the possibility to eradicate their problem, minimize hospital stay, minimize pain, that's what it's all about, right?
We really want to push the envelope a little bit. And when we start doing that, we don't know where we're going to be able to go with this. And I think that's really the excitement. The excitement is redefining what we're going to be able to do, or from what the standard of what surgery is now, so that with this we can redefine ourselves and really change the way things are done.
To me, what it represents, not the state of the art, we're ahead of the state of the art.
Right, so you see, this is a very interesting place for us to identify job and deploy a robot to undertake a task, right? And this scenario is relevant in Singapore because we have many hospitals with the state-of-the-art operating room, all right? And this one is also relevant to Singapore because we have many restaurants, and why not in future we deploy a robot integrated restaurant. Actually, I have a funny project student who have done some preliminary study in this area. Okay, so I hope that we could see a robot integrated restaurant in Singapore in future. All right.
So help could be at hand in the form of a robo chef that you can install in your kitchen. This kitchen wizard has been programmed to mirror the movements of humans slaving over a hot stove. But before you get too excited, it is 2 years away from going on general sale. But its Russian-born and UK-based creator believes it can be a tasty addition to any household.
You can cook in this module by yourself, by your hand. The model will recognize your movements, save it like a program, and after it's executed in the same way like you do without you. You can save this program unlimited times. You can save it for yourself. You can buy the recipe from any kind of chef in the world. Press the button, choose the recipe, load the ingredients, and start cooking without your help, and start watching how these people who generate the recipe cook.
Well, the Robo Chef is causing quite a stir, not just in those pots and pans that you saw. It has captured the imagination of quite a few of you, particularly on the internet. So most people do seem to like the idea, although some do say it takes the fun out of cooking. And connoisseurs do warn it will never replace the human touch.
We should never take the human element away from that. I still think nothing beats a person making your food who puts love into it and care and attention. And sometimes mistakes make great things. So I don't think it will ever take over human chefs and people cooking, because we love to cook. It's artistic. So for some people it's relaxing. For some people it's super creative. So I think it'll have its place, but I don't think we'll ever lose the human chef.
The issue is not whether or not automation will replace jobs in our context, because what we've done is create 120 new jobs in Silicon Valley.
What does the robot do?
The robots are doing the tasks that are unsafe, that are repetitive, that are boring, that aren't really human-centered tasks, like sticking your hand in and out of an 800-degree oven, 2,000 times a day. And the humans are doing human-centered work, collaborative work, creative work.
Like coming up with the cheesy E. I'm looking at Pineapple Express.
That's right.
The sweet corn pizza. I'm looking at some of your pizzas. That's what you do. So is this cheaper for you? I mean, The idea is that they're not going to take sick days. I mean, did you decide to go this way for a specific reason?
The problem that we were solving was how to get healthy food onto your table affordably. So yes, there's absolutely a margin play going on here. We're using automation and we're using technology to decrease some of our labor costs and occupancy costs, but we're reinvesting the surplus from that technology into better jobs.
Pizza's pretty cheap. Are your pizzas cheaper?
Our pizzas are as affordable as our competitors, even though a 14-inch pepperoni pizza is going to cost you $10, just the same as it would at a competitor. But even though it's got locally sourced, sustainably farmed ingredients, and it's the best quality.
Are your pizzas cooked in a central
oven or in a retail location, or can I walk in and get a pizza? Or is it all delivery? Tell me about that.
This is
and how much do these things cost, these robots?
Zoom is a delivery-only concept.
Delivery only.
So there is no physical storefront. Guess what that means? That means I don't pay 10% of my revenue in rent. That's another thing that we're doing to build profitability. All of the pizzas are prepared using our robot-enabled pizza assembly line in a central facility. But the way that we get the pizza to you is in a special vehicle that cooks the pizza while it's being delivered to your door. So it's always coming.
So what am I seeing going on here? I thought I just saw something come out of an
It's
oven.
getting cooked in the
Right.
video. There are people. They've got people.
Yeah.
So I
So
see the people, they're not getting cooked.
that's our par baking oven. So on a production
Oh, I
shift,
see.
early in the morning on our production shift, we're par baking.
Yeah,
That's
okay.
right. And then we're finishing them the moment that they get to
They
you.
get-
You can buy par-baked bread that you bring home and put in the oven.
Yes,
And then
yes,
you
yes,
talk
yes,
to the finished
So the pizza is cooked finally in the truck as it comes
Exactly.
to my house.
Yes, we have a sophisticated inventory sensitive routing system that tells the ovens within the truck exactly when to turn on, when to turn off, how hot to cook for, so that your pizza's cooked to perfection. Just the
I think
moment.
other pizzerias are doomed. Hey, every
All right. Okay.
If so, help.
And you can also find the job in school for robot to assist a human teacher, human tutor, in order to improve the efficiency of education. This video is quite interesting.
As the world outside school changes faster and faster, the majority of American kids are not being set up to succeed in the future that's coming. We're entering a world where there's not a lot of value on just kind of sitting there and doing what you're told. Increasingly, a computer could do that kind of stuff. We are eventually going to create a new model of education suited to the 21st century instead of the last half of the 19th century. This is going to happen. We're just trying to make it happen sooner. My name is Max Ventilla, and I'm the founder and CEO of Alt School. Working in Silicon Valley and being at Google and living here, it's kind of impossible not to have it shape your worldview and to believe that a mission-driven technology company can have an incredible impact beneficially on the world. And being a parent of young kids, there's really nothing I can think of that is more important than their education that I can be working on. As an entrepreneur, you have that startup bug. You need to work on something that catches you, and this was the thing that caught me. There's this problem, which is that the model that we have for educating kids, it is a mass production model. It's a factory model. It doesn't provide an individualized experience to kind of anybody. Every 45 minutes, kids switch to a different subject, and they open a textbook and they read the next chapter, and at the end of the week, they take a quiz. That experience is teaching kids how to think like computers, and that's not going to be very valuable when these kids actually grow up to be adults. If you're trying to fundamentally transform the education experience, that is not something that you can just kind of whiteboard with a bunch of research and a bunch of smart people in a room somewhere. You have to learn what that model looks like. For us, that meant immediately, almost from starting the company, opening a school. And then we opened 3 more schools, and then we opened 3 more schools, and now we're opening 2 more schools that are focused on personalized education. Each child defines their own experience to learn in a way that feels natural, takes advantage of their curiosity, and that doesn't try and corral them to learn this thing right now in this way. And that's where technology plays a foundational role versus a superficial role. There are 2 tools that fundamentally enable personalization in our schools. One tool is called the portrait, So this is a representation of all the things that are important about each child that different people can add to for curating a day-to-day education experience that's going to meet them where they are. That maps to a second tool, which we call the playlist, which is the kind of scaffold for each child's day. It's a to-do list and a calendar. It allows each child to decide, what order they do things, or they can decide what's on that playlist as they get older. It's allowing a child to have agency. None of us like being told what we need to do, when, where, how, with whom. There's nothing that's more demotivating than that. And if you're not motivated, you don't actually learn. There's no way to force a kid to learn. They have to actually go along with a certain experience. They have to actually think. What we see is incredibly promising out of the gates in the first 2 years. We're seeing much more than a year's worth of progress on kind of nationally normed tests. But as importantly, they're making progress on the social emotional pillars, things like grit, ability to work with others, ability to manage your time, to set goals that are going to serve those kids critically when they enter a world that's going to demand those kind of characteristics from them. I mean, my daughter's going to have a different life because this is the kind of school that she went to. And I love this Bill Gates quote that humans tend to overestimate what we can accomplish in a year and underestimate what we can accomplish in 10. First year, probably costs us $100,000 per student. The next year, it's like $60,000. The next year, it's like $35,000. This coming year, it's like $25,000. I think that when you get down to about $15,000 per student, now you're in the realm of the kind of median experience and lots of market.
All right, so this video is quite interesting, in which you could find opportunity to deploy educational robot. We could develop a robot which will assist the student to undertake personalized learning. All right, so this is another area in which we could find the job and the task for robot to perform. All right. Then with the massive deployment of robot in industry and the society, then what will be the transformation of a city, transformation of a nation in future? Then this is a video showing you some vision or prediction for year 2050.
70% of the world's population will be living in cities covering less than 2% of the Earth's surface. Never have cities been so challenged, and the trend continues to grow. This raises many issues. Pollution, infrastructure access, traffic congestion, mobility, safety, and the health of residents are only a few examples. The development and combination of new technologies, such as the Internet of Things and artificial intelligence, offer a multifaceted solution, the smart city. Smart cities are hyper-connected cities, technologically equipped to improve the lives of their residents. In Mexico, some neighborhoods are still struggling to get permanent access to electricity. So the city installed sensors to analyze the use of electricity in various sectors, so as to optimize energy distribution across the grid. As a result, less frequent power cuts and better distributed energy. In the United Kingdom, the city of Bristol created the Data Dome, a public platform where information on traffic, air quality, noise, or even the city's governance can be shared. They want to grasp the city's pulse by exploiting this data and give local players, citizens, and entrepreneurs the means to build the smart city that truly suits their needs. At AXA, we want to provide our know-how to enable public authorities, businesses, and society as a whole to better anticipate the future and thereby protect all actors living and creating the cities of tomorrow.
All right. So in this video, you heard this term, Internet of Things. Things basically refer to sensor and actuator. And in a broad sense, you can treat a robotic arm as a mega actuator. Actuator does not mean a single motor. You put the robotic arm or mobile base together. So actually, you can consider them as a mega actuator. Therefore, Internet of Things include Internet of Robot, all right? So that's about the purpose of task planning. So you understand, with the job as an input, then we should have a module which to identify tasks, possible tasks for human being to perform or for robot to perform in order to achieve the job. Okay, now we zoom in into the input to task planning module. Then what should be the input to task planning module? And obviously the input should be the job description in the form of a natural language. Natural language means a human language. Okay, now the challenge will be, could today's robot understand human language? If not, then human being must help robot to do task planning. All right, so that is an issue for you to think about. All right, and then since the input is a task, a job description, and what should be the key information content inside job description? And the answer will be these three key information. Information number one is the outcome of the job to be achieved. And this picture show you humanoid robot challenge organized by DARPA. Okay, the job is very easier to win the competition, to be the winner, okay, or to be the first to reach the destination, to be the first to earn the maximum point. Very simple outcome, just to win the competition, okay, or produce a car, or produce a TV, or produce a handphone in big quantity, whatever. All right. So outcome of a job to be achieved. Then we must put the space constraint, because we must deploy, set up a production line to produce the product or to achieve the outcome, plus time constraint. Okay, how many products per year are you going to produce, etc. All right, so these are three key information to be specified inside a job description. All right. For example, if we take the manufacturing system as an example, okay, so you will see the job of a production line is what? It's very simple. The job is to produce a finished product which could be sold to the market channel. Okay, then input to this production system will be the product drawing plus engineering material. All right, so this is a typical example. Then in between, we could plan a series of tasks for to be aligned together in the production line in order to transform engineering material into finished product. Okay, you can either hire a human worker to undertake this task, or employ a robot to undertake this task. Once you employ a robot, then you have automated equipment and control system, etc. All right. And here just show you one example of a manufacturing job. The job is what? The job is to produce aircraft. Okay. So we have this idea in mind. Then we come out the drawing. We have the key, the part drawing, then we fabricate all these key components, then we do assembly, then finally we get this finished product, and this product could be sold, okay, to the market, okay. So this is a typical example of a job, okay. And the input, obviously, you see, should be the product drawing, okay, product drawing, and also engineering material. All right. Here's a second example. The job is produce this type of service robot, then from drawing to key system to key component. Then we have machining the part. Then we do assembly, and finally we have this product as an output, which could be sold, okay, could be sold to the market, etc. Right? Okay, then once we know the input, obviously in this case the input is a part drawing plus engineering material. Okay, then what will be the output from task planning? The output from task planning will be the description of the task. Okay, so input will be the description of the job. Okay, so from here you see you can write down the description of the job from part drawing, engineering material, all the way to the finished product, which could be sold to the market, etc. Okay, then output from task planning will be the series of the tasks, okay, to be performed by robot, by human being, or by other machine, so that the job could be accomplished, okay, together by all these tasks. So therefore, you see, for task planning module, input is a job description, output will be task description, okay? So then, what should be the task description in manufacturing system? So actually, task description in manufacturing system are the internal output, because external output from manufacturing system are the finished product. So everyone knows, okay, we treat manufacturing as a system. So you have an input, so you have an output, then you have an internal process. So all these things work together. Basically, they accomplish the job. The job is to produce a product. Okay. Then how about the internal output? Internal output should be the planning of a series of tasks. Okay, for robot to perform or for human worker to perform in order to achieve the output of a manufacturing system or external output of a manufacturing system. All right. So internal output will be all this manufacturing process and the assembly operation. All right. Then for manufacturing process, so this is a tree structure, okay, for all the possible manufacturing process, okay. But okay, pay attention here. Manufacturing means mechanical manufacturing. In agriculture, when we grow vegetable, that is called as biological manufacturing. We also have chemical manufacturing. So here we just consider by default, when we talk about manufacturing, by default, it means mechanical manufacturing. Okay, so these are the major process involved inside mechanical manufacturing system. Okay, so you see we have a processing operation, assembly operation. From here, you can identify deformation process, material removal process, welding, and permanent fastering, like soldering, okay, something like that. All right. Okay. So here, I just list down these 5 typical or most popular type of a job in manufacturing. First one is deformation process. Second one is material removal process. Third one is a solidification process. And the fourth one is assembly process. And the last one is material handling process. All these process could be done by today's industrial robot. Okay, this is why they are popular. All right, so we can deploy an industrial robot to undertake all these tasks. Okay, process here means task in robotics, because in the terminology of manufacturing and the production, we use the keyword process. Then to robotic cost, process here means a task which could be performed by robot or to be operated by robot. All right, and here you see, give you an example about the deformation process. You have this forging process and rolling process. So you see, use a tool roller to change the geometry of input material, then produce output material of a different geometry. We may also have this extrusion process. Okay, so you have an input material, you have an output material. Okay, their geometry are different. So this is the kinds of forging process. Then we have the die. Okay, and inside the die we have a cavity. The cavity has a geometry. Okay, then the output material will take up the shape of the geometry of the cavity of the die. And here you see the input material, then output will take up the shape of geometry of the cavity. All right. And this show you example of a material removal process. We have a turning, drilling, milling process. Okay, and sculpturing process, etc. All right. And this is a cutting. It's also, this process also belongs to material removal process. So we cut a hole, we cut the disc, we cut the rectangle, or we cut the workpiece in different shape, right? Okay, and this is also a material removal process. This is doing the polishing, okay, to polish the edge of metal part, all right? And this is a typical example of solidification process. You may heard of injection molding. So injection molding, we just inject material in liquid inside the chamber of a die, then solidify it, then cool, low down the temperature, let the liquid to cool down to become a solid, then open the die, then we produce and finish the part. All right. We can also do the sand casting. Okay. So we create the cavity inside the sand, then pull in the molten metal and let it to cool down. Then we have a solid material as the output. Okay. So all this process could be operated by robot. So therefore, these are the tasks for robot to undertake. But here you see we have already a robotic arm. So immediately you know, okay, you can deploy robot to undertake the task. And for this one, you can also deploy robot to do the task. Okay, we can consider painting as a kind of solidification process because we spread layer by layer paint on the surface of a part. Okay, and the pen at the initial stage is in the state of a liquid. Then after that, then the pen will become a solid. All right. And okay, so this is also painting. It's a solidification process. Okay. And the last operation in the production line will be assembly. So we put all the parts together, then we see the final product like the airplane and the vehicle, etc. Okay, and we have seen this assembly process. You can treat it as an assembly process, right? And welding is also belong to assembly process. Welding is to join two metal together permanently. And this is to mount the wheel onto the body of the vehicle. So this is a typical example of an assembly process. Okay, and this is a material handling process. And at the output of a conveyor, we have finished the product. Then we do the pick and place. So we pick up the product and place it on top of the pallet. Okay, then this pallet will be shipped into the warehouse for storage and for the shipment to the buyer, to the customer, etc. So here, this is the typical station for material handling. Okay, and this is also a material handling process. So this is a simulation done by our student. So this is the typical example of pick and the place. We pick the bottle with liquid inside and place them inside the empty box, then ship out the empty box to the customer, to the buyer or distributor or something like that. So you see, okay, for each cycle of a pick and the place, okay, So you see the robot will follow, okay, specific path or trajectory, all right? Then this robot just repeat the similar operation, okay, one by one until the box is become full with bottle, all right? And you have seen this one. This is also a typical process of doing material handling. All right, so we move on. And here is another example of doing material handling with the coordination among the three robotic arms. All right, so you see, so for task planning, we have a job description as an input. We must produce a task description as an output. Then how to transform input, which is a job description, into the output, which is the task description. So then we need to know what is the process which will enable us to achieve task planning. And here we may consider two scenarios. The first scenario is to do task planning by human being. And the second scenario is to do task planning by robot, okay? If we deploy a human being to do task planning, and then the scenario could be described in this way. For example, person A is in charge of writing down the job description. This will be the input to task planning. Okay, for example, person B is a manager, is a boss, okay? So he fully understands what should be the job, okay, to deliver by a manufacturing system, okay? Then he just use a human language to write down a job description and either pass the written description to person A or speak to person A, okay? Once person A receive a job description in the form of a written document or speech, then person A will try to understand the meaning of the job description. Then based on his experience, he will plan a series of tasks to be performed either by human worker or by robot, all right? So this is a typical scenario of doing task planning by human being, okay? So here I just show you some activity which involve in task planning, which will be undertaken by human being, okay? So for example, you may heard of this name CIM. CIM means computer integrated manufacturing. So we have an information system which will store the part join to be produced. And CAM is a computer assisted manufacturing. So then we store the information about the internal production capability. For example, numerically control the program and software to do the scheduling for the production and the allocation of input engineering material. This we call manufacturing resources, etc. Okay, then this CAM will also undertake the handle process control, quality control, shop floor control, inventory control. All right, all these things. Then for the business activity, how to take in the order from your customer and how to send the bill to your customer in order to get to receive the payment, etc. Then how to pay your worker, like your internal worker, etc. All right. So for us, our intention is focused on this one and this one, product design. Okay. So we must have a part join as an input to manufacturing system. Then we can deploy the task, okay, in the production line. So that will be the factory operation, right? So once we produce a product in big quantity, then this will trigger business function, okay, trigger the marketing and the sales activity example, all right, okay? So first, we need to have a part drawing. Okay, so this should be the job of design team in your factory. And then here just show you example about the explosion diagram, which are related to a specific product. Okay, any specific product. Okay, and here you just need to pay attention to the letter M. M means in-house manufacturer. P means purchase from your supplier. From here you see, okay, as long as you are not going to purchase all the part, okay, from your supplier, then you need to organize manufacturing process, okay, internally, all right? So since we are going to produce some part internally, then we need to, okay, build up the list, okay, on daily basis, what will be the part to be purchased, what will be the part to be produced in-house. On weekly basis, send answer, and the monthly basis and the yearly basis. Okay, so we must come out the data information about this knowledge. Okay, once we know, okay, on daily basis, weekly basis, monthly basis, yearly basis, what will be the part to be produced internally. Then for each part to be produced internally, then we need to know, okay, what will be the basic process in order to produce this part? What will be the secondary process to produce this part? What will be the property enhancing process to produce this part? What will be the finishing operation to produce this part? Okay, then we must come out a table with these 3 columns. All right, then we tick. Okay, maybe for some part we just do basic process, and then without these 3 subsequent process, etc. So you see, for each part we must come out such table. Okay, so obviously you see this must be done by human being, and in future we could develop a robotic program to automate all this planning activity. Okay, then after that, then we can start to schedule the execution of this table of planning or product making table. Okay, so and this work schedule, basically you see for here, just show you an example. Let's say we have this part is a valve. Okay, and this valve will undertake, you see the turning and on the face and the reverse. Okay, then undertake the drilling and the milling. So you will see turning, and this also is a turning, then drilling, milling. Okay, so then we must put the schedule, give the detail, what is the starting time, end time, and the settling time. So you see the setup time, cycle time, okay, and then which machine to use to do the drilling. Then for this turning 1, turning 2, we'll use the same machine, okay, machine number 325. Drilling, we'll use this machine. Milling, we'll use the same machine, etc. You see, we must come out all the detail, okay? With all this detail, then we can supply this detail to human worker or to robot to actually perform the task, okay? And this video shows you the scenario of making use of a human worker to undertake
Roman DT is manufacturing everything from industrial printers to milling machines to vinyl cutters, using a single worker to assemble a product with thousands of parts from start to finish. These one-person work stalls, however, have a lot of digital help. A range of high-tech gadgets from 3D graphic monitors to digital screwdrivers help workers make every one of the company's 50 products.
約2日間にわたって組み立てに必要な基本的なスキルを身につける研修を専用に設けられたトレーニングルームで受けてもらいます。研修後は比較的短時間で組み立てすることができる小型のプリンターや小アッセンブリー、つまりユニットの組み立てから始めてもらいます。組み立てするにあたって、ネジ類の消耗品に関しては 部品供給ラックから、取り出します。で取り出すとパソコンの画面には、電気ドライバーでビス止めするように
The computer keeps track of every step, ensuring correct components are used and the correct number of turns are applied to a screw. Workers' speed and efficiency are monitored, and bonuses are awarded based on productivity.
そのパソコンで、記録された工程の履歴をもとに早い人の作業っていうところはどういった工夫がされているのか、肝骨があるのかっていうところを、現場を管理しているスタッフが中心になって、その膨大な生産ログを使って、しっかり分析して、分析した結果を教育であったり、実際パソコンの画面で表示される、作業指示、作業コンテンツの方に落とし込んで、全員の底上げをして、ばらつきを抑制したりという活動を行っております。
While cell manufacturing, as it's called, isn't new, Roland DG says the use of digital gadgets speeds up production time, lowers defects, and helps it keep workers motivated in a market crowded with competitors. At the end of the day, the computer displays the time it took to complete the job and even gives workers a pat on the back,
お疲れ様でしたと。
which means you must be tired, and we thank you.
All right. And once we have this work schedule planning, okay, in the previous video, we can hire a human worker to undertake all these tasks, okay? But for us, our intention is to employ automated equipment or robot to perform the task. Therefore, then we need to know how to deploy a robot and to develop the robot which could be able to understand the task description and automatically perform all these tasks. All right. So then come to this question. Will today's robot be able to take the job description as an input and automatically plan task description as an output? Answer is what? Answer is no, because it is still a challenge for today's robot to understand human language. Okay, so therefore we must rely on the assistance from a human being in undertaking task planning. Okay, so then, however, we must do research in order to make a breakthrough, okay, in this area, so that in future, robot will be able to understand human language, okay. The last video basically is to show you, okay, we must invest in this direction. Why? Because there are opportunity, many opportunities, okay, in future.
We think the main technologies that contribute to the factory of the future could yield over $500 billion of savings, which partly will be split between consumers and partly with equipment manufacturers. There are three characteristics that will define the factory of the future. The first one is a lot more things will be done virtually. Today, you still prototype a lot of things, and sometimes when you're going to production, you're still trying out layouts, which means from when a product gets first designed to when it finally gets to its end version that will be commercialized, you have a long lead time, which will be significantly reduced with new technologies. So product simulation, assembly line configuration, optimization, a lot of those things will start to be done in the virtual world. The second key characteristic of the factory of the future is the fact that it allows more human to machine collaboration. So for example, today industrial robots work completely separate from human operators. With collaborative robots, commonly known as cobots, you will be able to allow the operator to work alongside the robot and each other to adapt these tasks accordingly. And the third thing is there will be more real-time communication between enterprise systems and the factory floor and a two-way flow of information. which will allow for real-time optimization of the factory, remote control and monitoring from anywhere within the enterprise, not necessarily from the factory floor. Naturally, with all the focus on automation and cost savings that comes with the factory of the future, there are increasing questions about what this means for labor. We think what it means is that manufacturers will be more location agnostic in where they locate their capacity. They will be more focused on where demand is and where the best supply chains are, rather than on labor costs necessarily. We think what the factory of the future will result in is a very significant change in business models for both manufacturers and equipment makers for decades to come.
All right, so from the last video, you see this term, cobot. Basically, it means in the short term and the medium term, we could let a robot and the human worker to work together. Therefore, the collaborative aspect of robot is quite important. All right, so let's talk about this first lecture on task planning. The key takeaway from this lecture is for you to understand that there are many jobs in manufacturing, in agriculture, in the society, and a job could be decomposed into a sequence of a task which could be performed by robot or by human being. However, the process of doing task planning must depend on the assistance from a human being, because today's robot have not yet reached the level of intelligence which will enable them to understand the job description. Okay, and from this point of view, so it means what? We want to make the robot and the human worker to coexist or work together. Okay. And in this way, we can leverage on the strengths of a human worker and the strengths of a robot, right? So that ends today's lecture. So I'm looking forward to seeing you in lecture 2 of module 1.